Hello, and welcome to this pair of odd ducks that I bought just recently. An Atari PCM125 12-inch monochrome white monitor, and a very old computer of which the specifications were unknown. But it came with an LED display and a turbo button, so I was immediately sold. Now, despite the fact that these two items were offered in the same listing, I never put two and two together, and I didn't think that this monitor was ever used with this computer, as you normally don't associate these Atari monitors with PCs. But I did notice an unusual video connector, a 2-row D-sub connector, meaning that it's probably going to be either an EGA or a CGA video output. I also noticed a lot of corrosion around the keyboard area, so I knew I would have my work cut out for me. So let's take a look. We have a 3.5-inch disk drive, which is mounted on a 5.25-inch drive bay. We have a big hard drive here, not so much in actual size, but in volume. We have a video card and your typical IDE controller card. Now, PCs from this era typically have these old Varta batteries that tend to leak, and as they are leaking, they put a lot of corrosion on the mainboard, eating away lots of the traces, and this one is no exception. But however, despite the damage, I did decide to boot the system just to see what it would do under these conditions. And after a couple of seconds, I noticed this. So as you can hear, there are 8 consecutive beeps, meaning that there is probably something wrong with the video card. So let's take a look at it. So this is a pretty interesting video card. It's an ATI EGA Wonder 800 Plus. So it's primarily an EGA card, but it's perfectly capable of doing CGA, Hercules, MDA. It can automatically scan what type of monitor is attached. But there's a lot of corrosion on the pins here, as you can see, so perhaps that's what was causing the beeps when we try to boot the computer. But I'm going to try it with a different Hercules card that I have here, which I know that works, so I'm just going to put this into the computer and see if it will boot. Moment of truth, let's turn the PC on. We already see something appearing on the monitor. And after about 10 seconds, I was pretty surprised to see this 386 BIOS boot screen, but it immediately disappeared, came back again, disappeared, so you probably get the idea. These frequent reboots are probably caused by the impacted traces on the mainboard, so let's get everything out of the PC, including this IDE controller, so that we can have access to the mainboard. Now, when looking at the ad, I wasn't quite sure what the top device in the case was, so I didn't even know that it was a 3.5-inch disk drive. It actually looked like kind of a tape drive. But this is a Chinon or Chinon disk drive that is typically put in a 5.25-inch enclosure. It also has this old style floppy connector that you typically see on 5.25-inch floppy drives. Now, the hard drive is also a beast. It's a Seagate ST157A, a 40 megabyte IDE drive from Seagate. Hard drive type 14, so no need to specify user type or do auto detection. It's just a great looking hard drive according to me. Caution, do not low level format. We're not going to be doing that, but we will be checking to see if the hard drive still works. And here we have the bracket for the 3.5-inch drive bay. So let's open up the case so that we can have access to the main board. Here we have the CPU, optional floating point unit. This is a 386 SX 16 MHz CPU. We have SIP sockets for memory. Now, these SIP sockets can hold 4 SIP memory modules. Now, a SIP memory module is actually something that predates the SIM modules that we are very much familiar with. It's also a 30-pin random access memory package, but instead of using the edge connectors that we know on most modern SIMs today, this one had 30 pins along the edge that you would need to place into these SIP sockets on the main board. It was very short-lived and only used in 286 and 386 based computers. But we're mostly interested in this area here, which is where the havoc has been wreaked. let's take a closer look at the battery now. So a lot of corrosion on the keyboard connector, behind the keyboard connector. So lots of traces impacted. The back of the mainboard looks very nice, so that's a good thing. So what you typically find in this area is that you'll have a lot of the power rails which are coming from the power connector to go into the various bits into the mainboard. You also have a lot of keyboard traces here that go into the keyboard controller. First thing we're going to do is we're going to turn this around and get rid of that battery. Now, unfortunately, here I lost some video footage where I was cleaning the initial rubbish from the mainboard, so my apologies for that. But I'm using white vinegar to clean up the corrosion. So as you can see, it's kind of sizzling away at this keyboard connector now, getting rid of the corrosion that you see on the mainboard, the green stuff that covers traces, but also various components, keyboard connectors, IC sockets, headers, even ISA connectors. So we'll just take a Q-tip, we'll go over the traces, we'll put it into the ISA slots here, which were also impacted by the battery leakage. So just give it a good cleaning, just don't overdo it, because you know the vinegar isn't a natural thing to be put on a PCB, but it does the job really well of cleaning up all of this corrosion. So don't be afraid to go in between these components. So here we have some discrete components for the keyboard interaction that feed into the keyboard controller chip. So we're going to be cleaning all of them really well, because I imagine that there will be some repairs needed in that area. You can also use isopropyl alcohol to clean up the mainboard a bit after getting rid of most of the corrosion. So it's actually like a combination of using white vinegar to get rid of the corrosion and then finishing it off with some isopropyl alcohol. Now I'm also going to be removing the keyboard controller with my special IC socket removal tool. The reason why I'm doing this is because I want to get a view on the pins of the IC, and I also want to see the traces which go underneath this IC socket. So the keyboard controller chip itself is in pretty good shape. I doubt that there will be an issue with it. A couple of pins are a little bit corroded, but they're not going to be causing lots of issues. I assume the chip is going to be okay. So it's just a matter of making sure that everything is clean, that the corrosion has been removed. So we can also use a toothbrush to go over the areas. For example, this keyboard connector here has a lot of green stuff on it as well. So using a toothbrush and some white vinegar gets the job done pretty easily. And again, we can finish it off with some isopropyl alcohol to give the board a nice clean touch. Okay, so now that we've cleaned the board a little bit, let's take a look at the damage that has been done. Take this trace, for example. You see this capacitor here? It has a trace moving to the left, and here it's still making contact. If we move away, we again have contact, but at some point it stops. So this trace is completely broken here. It's probably broken at this point here, where the corrosion of the battery has eaten away the entire trace. So we will need to fix that. Now other traces might seem corroded, but they do still work. For example, this one. So this is easily verified by a multimeter just by doing a continuity check. This trace here is broken. So at some point we're losing the connection on the trace, again due to the corrosion of the battery. So this is also a trace that we will need to fix on the main board. Now let's take a look at another trace. We'll start from here. It goes underneath the keyboard, comes back out on the other side, and notice that it's almost completely black. That means that the corrosion has eaten away everything. So there's no more copper here. So this will definitely give problems with the main board, because I suspect this is going to be a power rail. So in order to verify that, what we will do is we will take our multimeter, put it in fault settings, and use our probe on the test point to see what the voltage output is. And as we move down the trace, we're not seeing the minus 12 volts that we are expecting, but we're seeing minus 4 volts. So that's due to the trace that has been broken. So we can follow the trace all the way down here onto the ISA slot. And the ISA slot is also a good way to have some reference points on the main board, because the ISA slot is standardized, so every pin has its designated voltage. And if we look here, where we should have the minus 12 volts, which was coming all the way from the top of the main board into the ISA slot, we're only seeing 4 volts on it. Now you might be tempted to solder a wire onto this test point here, and then making your way to the other side, again attaching the wire to the test point and soldering the wire on it. But that will never make for a good connection. Now the proper way to do it is to locate the test point on the back side of the board and search for an associated solder joint. And we'll be using those solder joints to attach our wire. So we search for the solder joint, we add some solder to it, and we hook up our wire like so. We do the same thing on the top side. We attach our wire, and we should have a good connection now. So a simple continuity check will prove that the connection is now firmly established. And we will need to locate all of these broken traces. Now this is a process that can be time consuming, but using a multimeter you usually find these bad traces fairly quickly. And again, the process is the same. We've located 2 test points that have proven to be not connected anymore. So we flip the board around and we repeat the process that we've already done. We locate the 2 test points. Just imagine the trace going from this point all the way across to the other point on the other side of the board. And then we just look for a good solder joint where we can attach our wire. So this test point here will never make a good connection. So we just follow the trace to the solder joint and we select that one. Same thing on the other side. We look for the test point, search for the solder joint that's associated with it, and we select that. So these are the points that we're going to be using to attach our wire. So we just need to have a piece of wire now that we will hook up to the 2 solder joints. We'll add some solder to the joints here so that the wire will make a good connection. We do this on both sides. We take our piece of wire and we attach it to the 2 solder joints. And this will make for a lot stronger connection than if we were to do it using these test points. Now hopefully we were able to fix most of the voltage lines on the main board, so let's boot her up and see what she does. And we get this gate A20 error. These errors always relate to either the keyboard, the connector, or the keyboard controller chip. And wouldn't you know it, rookie mistake, we forgot to put it back in. So let's start the system with the keyboard controller in, and it does boot. It does a memory test. It prompts us to press delete to enter the setup, but we notice that the keyboard doesn't work. However, the fact that we do get the computer to post, that we do have a memory test, that we end up where we are now, means that most of the voltages are probably okay on the main board, so now we can focus on the keyboard. Now, the fact that the keyboard doesn't work can be the result of many things. It can be an issue with the keyboard controller socket. It can be an issue with the actual keyboard connector. Perhaps something is wrong internally with it. Perhaps the various pins inside a connector have gone bad or broken off, or faulty traces on the main board. But most likely it's going to be traces that come from the keyboard controller that can be followed here from the keyboard controller socket to the rest of the main board. So let's follow one of those traces. So this one should go to the 2nd pin on the bottom row, but there is no continuity. There is continuity here, but then all of a sudden the connection gets lost. So this is again a trace that we will need to fix. So I'm again taking a piece of wire. I solder it to the test point here that we just tested, and I'm going to add it to that keyboard controller pin, which was the 2nd one from the bottom. So I'm just going to be adding it here to make a clean connection. So let's just verify that this worked. And yes, we have continuity between the 2 pins. So you really need to go through all of the pins here to make sure that all of the traces are correct. For example, let's take this pin here, follow the trace. It goes to this test point inside the socket, and we see that we don't have continuity. And again, it's a matter of hooking up a wire. I'm sorry that this shot got off screen. So we're just going to trim our cable, solder it to the test point, and verify the continuity. Final issue that I saw was with this connection here that goes into this bottom resistor. After fixing that, I thought it was time to give the motherboard a go. So we put in the keyboard controller chip into its socket. We also cleaned the contacts of the ATI EGA Wonder 800 Plus because I'm dying to find out if this EGA card still works. So let's put it back in and fire up the PC. So we see our boot screen, which is good. We see the memory count, which is good. So let's speed things up a bit until we're prompted to enter the CMOS settings. And here we go. Bingo! We have a working keyboard. Can now enter the setup utility. So let's start by configuring our floppy drive A, which is a 3.5-inch 1.4 megabyte drive, and our hard disk, which is of type 14, which is our 43 megabyte Seagate hard drive. So let's save this and reboot. We now get a memory size mismatch, so we'll need to enter the setup again and notice how the extended memory size has been altered. So we'll save, reboot, and now the system should boot, which it does. Except for the fact that the hard drive doesn't want to boot for some reason. Which is strange because I was able to format it and copy over the system files. But let's try this again. So it's trying to start, and yes, we get the DOS prompt. So yeah, it needed 2 tries, I guess. But it wasn't too long before the hard drive started misbehaving again. Random read and write errors. It did have some bad sectors. And it did start to produce this really loud, annoying noise, so I thought it was pretty much toast. So just to make sure, I decided to open it up, and yep, here we go. These little white circles on the platters are definitely not normal, and a full-on head crash had occurred on this hard drive, making it completely unusable. Which is a bit of a shame because I really liked this Seagate hard drive. But not to worry, I still have a bunch of other old hard drives that would fit the system nicely, like this beautiful Western Digital, until I discovered a small abnormality with the power connector on this hard drive, which is almost completely broken off. So let's get the circuit board out of the hard drive and see what we can do. So let's take it off. There's a cable attached. It probably goes into the motor. So I'm just going to try to set this aside a little bit and see if we can get access to the actual connector. Now, as you can see here in more detail, 2 of the pins that hook up the 4-pin power connector have completely broken off. So we'll just apply some solder here to make a firm connection onto these 2 pins and then verify if it will hold everything in place, which it does. So let's put it back on, put the screws back in, and we should be good to go. So we need to configure our hard drive. We're going to specify user type, 1010 cylinders, 6 heads, and 55 sectors. Let's write this to the CMOS, reboot, go to fdisk, create a primary partition, allocate all of the space onto the partition, reboot, and try to format the hard drive. So I'm speeding this up. Obviously it's not going that fast in real time, but no bad sectors, everything seems to work. I found these old Dell MS-DOS 5.0 installation disks, so let's use that to install MS-DOS 5.0 onto this PC. So all we need to do now is reboot the system, and hopefully we should have a fully functional MS-DOS 5.0 machine. So it's loading up the shell. So MS-DOS version 5.0 is installed. We are pretty low on memory, so we'll need to do something about that, but our hard drive, our Western Digital 170 megabyte hard drive is working flawlessly, so that's a good thing. But all in all, after a good cleaning, I'm pretty happy with this build. The computer seems to be running fine. I've cleaned up the case. I think it looks pretty good. I did end up having to fix lots of traces, but I'm really happy with how it turned out and how I was able to get the PC up and running again. I know that these types of wires aren't ideal, but they were the only things I had in stock. I am pretty bummed out about the fact that the Seagate 40 megabyte hard drive crashed. I was really hoping to keep this hard drive because I really like the look and feel of it, and it fits the authenticity of this old 386 very nicely. I like the combination of that 5 1/4 inch, 3.5 inch disk drive. I like the LED display, the turbo button, the case in general. I think the Atari monitor also gives it an additional touch. I'm not really sure what I'm going to be doing with it. I'm sure I'll be featuring it in another video. It will need a memory upgrade in order for it to do something useful, but I'm sure we'll figure something out. So thanks for watching, and I hope to see you guys next time. Bye bye.